Hello, everyone. So I'm not sure that this is on the AP exam, but it is a very helpful alternative of finding volume. Okay, and we're gonna do an alternative method of finding a volume that is called the shell method. Okay, the shell method, and this is definitely not on the AB exam. Okay, so it's like a BC lesson, and the shell method is used when either the disc or the washer method does not work. Okay, and the shell method basically utilizes a cylindrical shell, a cylindrical and very thin cylindrical shell. And for a sense of what a cylindrical shell is, if you picture like a toilet paper roll, a very like an empty one with nothing on it, that is a cylindrical shell. Okay, so it is literally, if I would draw it right, this is a cylindrical shell. Okay? So before we start getting to any problems, first we need to find out a volume of a cylindrical shell, okay, and where it comes from. So let's say you had a function negative x squared plus 4, okay? And you want to find the volume of this region, okay? The volume of this region. Okay, so this region over here, I want to find the volume of it. Now you could either solve for y, okay, you can either solve for y and so if y equals negative x squared plus 4, you can either solve for y and use the disk method, or you could use the shell method, okay? And what the shell method does, okay, is that it basically adds up tiny cylindrical shells. If you had rectangles like this, okay, and you were to rotate it around, you would get tiny cylinders. Very tiny cylindrical shells, okay, empty cylinders that start to add up inside each other, okay? That would add up inside each other to get your volume, okay? So we literally form a cylindrical shell by rotating a rectangle about the y-axis. Okay, so if we were to rotate the rectangle, you would get your cylindrical shell. Okay, so we have this. Sorry, it's not very neat. Okay, it's never much of an artist. But this is our cylindrical shell we get by rotating our rectangle. Okay, so our rectangle has infinitely small thickness. Okay, infinitely small width as a height of f of x. Okay, so what is the volume of this cylindrical shell? Okay, so you can see that the volume of our cylindrical shell, okay, let's shade this in, is the volume of this big cylinder minus the small cylinder. So this starts to bring back stuff from the washer method. Okay, so we call this R. Okay, and this over here is, okay, dx. Okay, this is R and dx. Well, what does R represent, first of all? Okay, R, what does R represent? Well, R represents the distance from the y-axis to the function, okay, usually x, okay? So the distance from your axis of rotation, okay, this is your axis of rotation to the actual function, okay? And what we're going to do is find it in terms of r, okay? So this is literally equal to the volume of the big cylinder, pi r squared h. Okay, so this does have a definite height. And this height is equal to f of x. Okay, so if we were to look over here, the height of our cylindrical shell is f of x. So pi r squared h, okay? So immediately, let's just write everything in terms of x. So this is x, and this is f of x. So pi x squared f of x minus, okay, minus pi let's do that again. So we're going to define x as the distance from our center to here. Okay, so this is x. So the volume of our cylindrical shell, okay, will be pi times big R x plus dx. Okay, that's what I meant to do. Times f of x minus pi times x squared times f of x. Okay, the volume of the big cylinder minus the volume of the smaller cylinder inside. Okay, you can see that the cylinder, this forms like a cylinder on the inside. Okay, so you see it sort of forms a cylinder on the inside as well. Now, we can factor out pi times f of x. So pi times f of x, and we get x plus dx squared minus x squared. And now there's just a difference of squares. So what we get is pi times f of x times a plus b, so 2x plus dx, times a minus b. Okay, so x plus dx minus x, so that's just plain dx. Okay, that is our volume of our single cylindrical shell. Okay, and because we're adding a infinitely small length to 2x, and x is so much bigger than dx, because x is so much bigger than dx, we can just write, as dx becomes infinitely small, pi times f of x times 2x dx, okay? We still need to have that dx there because we're going to end up integrating this. We're going to end up integrating this. So this is our volume, our tiny volume, the differential of v, okay, the tiny volume. So we get, if we integrate both sides, we get v equals, you can pull out 2 pi from 0 or a to b, not necessarily 0, a to b of f of x times x times dx. Okay, and that is basically the integral formula for the shell method. Okay, so we literally just added, okay, an infinite amount of infinitely thin shells, cylindrical shells, and that will add together to get us our volume. Okay, so we get that volume equals 2 pi times the integral from a to b of x times f of x dx, where x is the distance from our axis of rotation to our function. And to see how this works, we're going to find, okay, that problem we did, the parabola, negative x squared plus 4, we're going to find the area of this region in 2 ways, the disk method and our shell method. Okay, so what is the volume of this region? Okay, this volume of the solid. So here's way number 1. Okay, let's solve it for let's solve it for x. So negative x squared equals y minus 4. So we get x equals the square root of 4 minus y. Okay? So we just turn it in terms of y. Okay, we're revolving it around the y-axis. So we have to turn it in terms of y. So we use the disk method. We get pi times r squared. Okay, so r squared 4 minus y times dy. Okay, this is our singular disk. And what do we get? Okay, so our limits of integration are from 0, y equals 0, to y equals 4. Okay, so we have the square root of 4 minus y squared. Now if we were to integrate this, you get pi times 4y minus y squared over 2 from 4 to 0. And because this expression is 0 when y equals 0, we only need to evaluate it at y equals 4. So we get pi times 16 minus 16 over 2 is 8. And we get 8 pi. Okay, we get 8 pi as our volume. Now let's see what happens if we use our shell method. So volume equals 2 pi times the integral of a to b. So first let's draw a cylindrical shell. Okay, so if we were to draw a cylindrical shell, now we're going to be integrating in terms of x. Okay, so I'm going to draw a red cylindrical shell. So what is our height? Okay, our height is f of x and our distance is x. So our distance, our radius of our cylindrical shell is x times 4 minus x squared dx. And what's our a to b? Our a to b is from 0 to x equals 2. So if we integrate this, 2 pi from 0 to 2 of 4x minus x cubed dx. So we have 2 pi. We take the integral, we get 4x squared over 2, so that's 2x squared minus x cubed. So that's x to the 4th over 4 from 2 to 0. And now, what do we get? We get 2 pi times 2 squared, that's 8, minus 2 to the 4th is 16 over 4 is 4. So we get 2 pi times 4, which is also equal to 8 pi. So we get the same answer no matter what we use. Okay, although disk method might have been a bit easier because of this much easier integral. However, you can't always use our friend, the disk method, as much. Okay, you can't use it as readily as you can the shell method. Okay, and one instance in which we could use the shell method is right over here. So if, let's say we had the integral, so not the integral, the function e to the negative x squared. So we have f of x equals e to the negative x squared. And let's say the region from 0 to 1 was revolved around the y-axis. Okay, so it's revolved around the y-axis to form a solid. Okay, so it forms a solid. So what is the volume of this solid? Okay, Now, what happens if we try to do disk method? We have y equals e to the negative x squared. So we have ln y equals negative x squared. And you get x equals the square root of negative ln of y. And that is going to be a problem. Okay? Because if you integrate this, okay, well, you're going to get a integral of ln, okay, something which we do not know yet. And even if we did know, would be a nightmare to integrate. So the shell method seems a lot more preferable. So let's construct a shell, okay? So if we drew a cylindrical shell, okay, like this, a cylindrical shell. Okay, and we wrote down our formula. Okay, the volume equals 2 pi times 0 to 1, 0 to 1 of our radius x times the function f of x dx. Okay, so what is our radius? Okay, so the distance from the axis of rotation to our function will simply be x. Okay, and the height will be f of x. So if we were to write it like this, you write it as 2 pi times a definite integral from 0 to 1 of x times e to the negative x squared dx. Okay? And this integral is kind of easy to evaluate because you can do a quick u substitution. Okay, so if u equals negative x squared, du equals negative 2x dx. So all we need to do is multiply times by negative 1/2. Okay, so we can introduce a negative 2 into our integrand, okay, inside the integral. Okay, so let's not put any limits yet. So you have negative 2x e to the negative x squared dx. Okay, this essentially becomes negative pi times the integral of e to the u du. And that equals negative pi times e to the negative x squared. E to the negative x squared from 1 to 0. Okay? And our volume, okay, we got is negative pi times e to the negative 1 minus 1. And the quantity inside our parentheses ends up being negative. Okay, so what we can do is remove all the ugly negative signs and make it look a bit nicer. And we get our final volume as pi times 1 minus 1 over e. That's the exact volume. And you really could not have, done this without use of our shell method. Okay? Because the disk method would have been really, really difficult. And turns out this approximately equals 1.986. Okay, and that's the exact volume. So using the shell method, we were able to find volume using our shell method. Thanks for watching. If you have any questions, please make sure to ask in the comment section. Like this video and see you later.